perfect.
Perfect. Wow.
Not quite
Excellent.
perfect, but could be better.
Okay. So any questions from the midterm? So I have my usual office hours tomorrow at 7 o'clock to 9:30. So come catch me then if you want to
Do you ever drop it?
talk about midterm or other things. I ripped it from somewhere. So I posted an announcement November 13th. I'm not having class. Okay, so I'll be out of town that day. And that's my last sort of unscheduled absence. So after that, everything should be business as usual. But that's kind of in between things. So that's a Wednesday. So I'll have regular office hours that week. So let's review past two ODPs. So the previous ODP to the one that you did Friday, 416, we were removing all the X's from a string. And we already looked at code for doing that, and this was a solution. The one that you did on Friday, 417, was almost the same thing, but you were only supposed to remove the first string. And so here's a solution for this. And the main trick here is using what we call a flag. Okay, a flag is generally something that you use to indicate that something has happened when you're not ready to use that information at that moment. So something occurs, but you're not ready to act on it until later. So you set a flag, you put a flag up in the air and say, hey, this thing happened. And then later on in your code, something looks for that flag and says, oh yeah, that thing already happened, or no, that thing hasn't happened yet. So in this case, the flag is called done. And what I'm thinking of done as meaning is we've already removed the first X. Okay, we're done with the X removal piece of the assignment. So done is originally 0, and I'm using 0 to mean we're not done, and 1 to mean we are done. Okay, so it's a flag. And the logic is basically the same thing. We loop through the input string. If the input is not X, we copy it to the output string. But we also check to see if that done flag is set. And if the done flag is set, it doesn't matter if the character is an X or not. We're just going to copy from the input to the output.
You don't need brackets for that first if?
Brackets?
Right.
Oh, curly brackets?
Yeah.
Yeah, normally I would put them in around, yeah, so I asked people to do this and I didn't do it. But normally we would do that.
After the
We'll
out?
put it in the correct spot.
Oh, sorry.
Yeah, so do it like that. But if you don't have brackets, technically it works, but it only does one statement.
Oh, okay.
So it's just doing that. But I tell people to always put in brackets anyway. So it's the same code, except that we use this flag to say if the flag's set, let's just go ahead and copy the character regardless. And then there's an additional line after this which says if the character is an X, let's set the flag, saying we've already seen an X. And there's three things I want to point out in here besides those algorithmic aspects. The first, I just say if done or, right? This is not if done equals 1, but that's what I mean. If done equals 1 or if the input character is not an X, let's copy from input to output. But remember, C has this way of treating integers. If an integer is equal to 0 and you use it in an if statement, it's considered false. If it's non-zero, it's considered true. So even though technically what I should say is if done equals 1, right, I can just get away with saying if done. Because I know since I wrote this, done is either 0 or it's 1. And it starts off at 0, that's false. When I find an X, I set it to 1, it's true. So that's just a coding shortcut. But you'll see that a lot in code in C, if variable name. And it's really useful for flags. Okay, the second thing to note is really I only need to set done equal to 1 the first time I find an X, right? It's just a flag. It's true or false. It's saying, have I seen an X? So the first time I see an X, I should set done equal to 1. What this statement actually says is anytime I find an X, let's set done equal to 1. So if I have 5 X's in my input string, I set done equal to 1 5 times. Does that do any harm? Absolutely not.
Performance-wise, though.
Performance-wise, well, the extra if might actually take more time. It's hard to say. But in the end, right, the behavior is exactly the same. And this is just a coding shortcut. This is just me being lazy, right? If done's already 1, if I've already seen an X and I decide to set it to 1 again, doesn't do any harm. So you'll see things like that, and they might not make sense, like didn't we just want to do it the first time? Well, logically, if it ends up with the same result, that's okay. So that's another slightly odd thing in here. The third thing is this for loop. And almost always when I write a for loop that iterates over a string, it's I equals 0, I less than string length, I plus plus. Here it's I less than or equal to string length. Why would I do that?
To catch the null terminator?
To catch the null terminator. Because I know that if I go up to string length minus 1, that's the last character of the string. If I go one more spot, it's the next thing after that, which is the null terminator. And this is a really cheap way of making sure that I copy the null terminator from the input string to the output string. And that null terminator is not going to be equal to X. So this statement will fire, and in bracket iloc will be the null terminator, and out bracket outloc should be the correct place to write that. And so I don't have to put the null terminator in at the end after this while loop. This actually gets done the last time through the loop. It's just another trick. Now you could write this in a way that would be clearer to read, where you would do all these things separately. Right? You'd say if done equals 1, then do this. You'd loop up through string length minus 1, and at the end of the loop you'd assign the null terminator to the output string, and maybe you'd set your flag if it wasn't set and you found an X. Right, so your code can look a lot of different ways. But that works fine. All right, so questions on ODPs, recent? So we'll probably get back to ODPs on Monday. We'll take a break for this week, but Thursday, tomorrow, I'm going to talk about PA4 since I'm not here Friday. PA3 is still due Friday morning, okay, but I'm going to start talking about the next one a day before that, just to give you an overview of it and let you have the weekend to work on it. And that's going to be a C program, and it's going to involve a lot of string processing, things like what we're playing with here. So I'm going to put some more ODPs up next week that'll help you with the kinds of things we're doing in PA4, including working with two-dimensional arrays of strings. So we're going to make our own version of an argv, basically, an array of strings, yeah, which will be good. All right, let's talk about GDB. So let me start building a list of useful GDB commands. So here's some code from the calculate ODP that we did, where we were taking in a string like 2 star 3 and trying to evaluate that as an actual number and then print that out. And so here's my code, and I'm not doing error checking, but I'm parsing out the input string, doing an operation and returning that. And I'm parsing the string 2 star 3, but when I run it I get a 0 instead of a 6. So let's do gcc-g-o calc.c, and let's debug this. So compiling gcc-g, and then whatever else you would normally put in your compile. Right, so this is compile with GDB support. And then to actually start debugging your program, you say GDB and whatever the name of the program is. And we get all of that stuff. Remember, it says reading symbols from calc done. That's good. That means it has debugging information. And then we get a prompt in parentheses GDB. That's the prompt for user input. So that means it's waiting for us. All right, so what can we do? We can say start. That basically begins the debugging process. And you're always going to say that in the very beginning. So start. That starts debugging. You can say list, and that'll show you the source code. And if I say continue, it'll go ahead and run the program from its current place, and the whole program runs and it prints out I equals 0, which we know is incorrect. It should have said I equals 6. But if you decide you want to just see what happens when the program runs, just say continue. So that's continue running. And remember, in GDB, you only need to specify enough of a command to be unambiguous. So the only command that starts with cont is continue, so I can just say cont, and that means continue. If I type a p, that means print. So I don't need to say print over and over. All right, so I ran my code and it should have said I equals 6, but it said I equals 0. Let's start this again. So I don't have to exit, I can just say start, and it'll go back and start running from the beginning, and again it gives me the GDB prompt. Okay, it's always showing the line that's about to execute. It's about to execute I equals calc. So what I want to do is I want to run my code one line at a time and watch what's happening. Because I know if I just call calc and come back, it's returning the wrong value. So I want to see what's going on inside calc. And there's two ways to single step through. There's next and there's step. So next is what we usually call a step over. And step is what we call a step into. So here's the difference. Both of them basically say execute one line of my program. But if that line happens to be a function call, next we'll go ahead and run the whole function, and then it'll come back to the debugger. Ergo, since we're about to call calc, if I say next, it will execute the entire call to calc, and it'll come back and it'll show me the next line 10. Step, on the other hand, says if this is a function call, just go into the function and wait. Come back to the debugger. So if I say step, it gets into the first line of my calc function, which is the curly bracketed line 14, and now it's waiting for more instructions. So I'm inside the function that's being called, and I can debug that function. So step goes into a function, next just skips over the function. It executes the whole function before it comes back. So line 14 is the beginning of my calc function, right? And it's showing me that calc was called with an argument buffer. Well, you know, I defined integer calc char star buffer. So it's showing me the value of buffer, which is this hex 555 thing. And it's also showing me the value of it as a string. It's the string 2 star 3, which makes sense because that's what I passed as the argument to calc. So we're about to start executing the calc function. Okay, so I'm going to say next. And it doesn't execute anything for integer n1, n2, character op, integer, result, blank line. Those don't correspond to executable code. That's stuff the compiler used to say, oh, when I see OP, it's a character, right? But there's no translation of those things into assembly language instructions. So the first instruction it's going to actually execute is this call to scanf. And I can double check these arguments. So buffer is 2 star 3. N1 is junk. OP is 0. N2 is junk. Stat is junk, right? Because this instruction is not executed yet. Okay, so I want to execute this call to scanf. Do I want to say next or step? I want to say next because I don't want to debug the scanf function. I want to call scanf and I want to come back to the next line of my program. So I'm going to say next or just n. And now scanf has returned. So now if I print n1, that's a 2. If I print n2, that's a 3. If I print my operator, that's a star. Okay, scanf has broken up my input buffer, which is still 2 star 3, and it's populated n1, op, and n2. Right? It found all 3 patterns I was asking for. It should have returned a value of 3, which it stored in stat. If I print stat, stat's equal to 3. Everything is great right now. Okay, we totally understand what scanf did. It did what it was supposed to do. We're all set. Okay, if operator equals plus, result equals n1 plus n2. If operator equals minus, if operator equals star, then it should say result equal to n1 times n2. Well, we know the operator star, so let's execute that instruction and let's print result. Hey, result is 6. 2 times 3 is 6. This is looking good so far, right? Okay, if operator equals slash, it should skip that. And then it should return result. And now I should have been set equal to that return value, but it's equal to 0. So even though our calc function returned 6, I ended up being 0. Okay, something's weird. All right, when you're debugging code, you've got to sort of be willing to suspend your belief in logic and order. Because if you look at your code, and it should be doing one thing, and you run your code and it does something different, there's a disconnect somewhere. Okay? And you gotta accept that. You gotta accept that the code is doing something different from what you told it to do. Because in reality, you probably didn't tell it to do that. You told it to do something different. But you can't really find that unless you're willing to say, okay, there's something here I don't understand. Okay, so I'm going to start this function again. And I'm going to step into my calc function, and I'm going to next through. And I'm going to print the value of result after that n1 times n2. That is definitely a 6. And I'm going to come down here. It's about to return result. Let's double check what it's returning. It's returning a 0. So we knew there was a bug because when we ran the program originally, it should have said I equals 6. It said I equals 0. What we've done now is we've pinned that bug down to a really small section of code. Somewhere around line 24, something is going wrong. So let's go back to the start. And if the program's running, it'll say the program's already running. Do you want to start from the beginning? You just say yes. And let's step into our calc function and let's next through. And if we look at this, result is equal to 6. We know that when we execute line 24, result's going to change to a 0. Well, it says if operator is a slash, change result, but we know operator was a star, right? So let's execute that instruction, and result changed to a 0. It must have done that if statement. But if we look at operator, hey, guess what? It's not a star, it's a slash. And since it's a slash, that's why it did that result equals n1 over n2.
Does it need the second equal sign to make it a check instead of assignment?
Exactly. So if OP equals quote slash, that's an assignment statement. This is the hardest bug in C to find. Right?
What?
This says set OP equal to a slash, which makes it logically true because the slash is not equal to 0. So this is if parentheses non-zero, that's true. So it sets result equal to n1 over n2. So you could stare at this code for a long time and not necessarily see that you should have had a double equals sign. Unless you're me, who's done this like a million times and is tired of making this mistake. So I always look for that now, right? But when the debugger, it forces you to look at this line of code and say something is happening here that's different from what you think. And if you know that there's a problem in one line of code, it's a lot smaller thing to sort of break down than your whole program, right? And in the debugger, because we can look at everything before and after, right, we could see in this case OP changed to a slash. And once that happens, then you're going to see it immediately. Why would that previous statement have said OP equal to slash? Oh my God, I can't believe I did that again, right? So now you go through and you change those double equals and you run your code and it works great. So this is one thing that GDB does for us. It lets us look at our code while it's running, and we can examine variables. We can step one thing at a time. We can make sure the flow is correct, loops happen the right number of times, and so on and so forth. And you know, an alternative would have been to print out the value of every single variable after every single instruction, and you can do that, but that's a lot of data to stare at. I've done that. And it works, but if you can be more tactical in what you're looking at, that can help. All right, so that's one typical use case of GDB, and we're really just using just a few commands. All right, start, list, continue, next step, print. That's really all we used. And you can get pretty far with those. All right, and I'm going to Control D, and it says it's still running. Do you want to quit anyway? I'll just say yes. All right, so here's a prior ODP. This was the ODP that removes the letter X from a string every time that it occurs. It removes all the X's from a string. And here's some sample code. And so there's some test code. I've got hello with an X in the middle. I'll call my remove function. I'll print out the value of temp. And I'll run it, and it looks like it works great. It removed the X from the middle of HELO. So when I posted ideas for debugging code on paper, right, and I said write down the variables as you declare them, and when you change the value of a variable, write that down next to it, and keep track of where you are in the code and so on. But I also made the comment, if you don't know the value of a variable, fill it in with question marks, right? If it's an integer, fill it in with some crazy value. If it's a string, fill it in with question marks. Because we don't know what the values of these variables are initially. And in this case, we don't know the initial value of temp. We've said it's an array of 120 characters, but we haven't given it a value, so it could have anything in it. So my suggestion for debugging on paper was give this thing an initial value of a bunch of question marks. So I'm going to use string copy. It's a string.h function to copy a bunch of question marks into the temp array. And now when I run it, it doesn't work the way I wanted it to. It removed the X, but it added a question mark to the end. So now we've got something that is not working correctly, right? And if you wrote a main program that did a whole bunch of different tests, you'd see something similar happening. And if you work through this on paper and you assume temp was originally a bunch of question marks, you'd see something happen. But let's go ahead and GDB this. All right, so I'll start it, I'll next. I'm not going to debug the string copy function, so I'm just going to say next. But let's look at temp before we do this. If we look at temp, it starts off with 24 null terminators. Okay, this is why we weren't seeing a problem before. Because even if we never wrote a null terminator ourselves at the end of the output string, it's got 24 null terminators sitting there to begin with. And if I load the characters HELO into those first 4 spots and I completely forget to add a null terminator, it's still going to have a null terminator on the end because it's got those to begin with. Just because that's how it happened to be. Not through any fault of our own. So when I do the string copy, and then I print out temp, now it's got a bunch of question marks in the front. And if I don't put a null terminator, it's not going to see a null terminator until it goes through all those question marks and gets to the first of those 16 nulls that happens to be sitting in memory. So this is going to expose a bug. All right, so let's step into the rem function because we want to debug that. And it's going to set k equal to 0, and it's going to set a equal to 0, and now we're sitting at a for loop. Okay, so let's double check. Our input is HEXLO. Our output is bunch of question marks. A is 0, k is 0. So let's start debugging. So let's say next. So it says if in bracket k is not equal to x. Okay, let's print out k, it's a 0. Let's print in bracket k, that's the letter h, that is not equal to x. So it should execute the body of that if statement which says set out a++ equal to in k. Okay, let's print a is 0. Let's double check out. Out is question marks. Let's execute this statement. And now a got post incremented to a 1. And out is an h followed by question marks. So what did it do? It read the first character of the input. It copied it to the first character of the output. That's great. And now we're back at the top of our for loop. And k is equal to 1 now. And that's the letter E, so that should get copied to the output. And now if I look at the output, it's an H and an E, and A is equal to a 2. We got 2 characters in the output. And we're back at the top of our for loop, and k is equal to 2. If I look at in bracket k, that's an X. So it should not copy it. And sure enough, it doesn't. It goes right back up to the top of the for loop. So now k is a 3, a is still a 2, and our output is still just the h and the e. Everything's perfect, right? All right, if in bracket k is not x, let's look at in bracket k, that's the letter L, so that should get copied to the output. And the output is now HEL, and a is equal to 3. Still good. Back to the top of the while loop, k is 4. That's the letter O. That's not equal to the letter X. So that should get copied to the output. Print the output, it's HELO. Print the value of A, that's 4. We've got 4 things in the output. Okay, we're back to the top of the for loop. K is going to get incremented. Right, it's a 4. We know that in is HEXLO that has a string length of 5. So once k gets incremented, it should kick out of this for loop. And we do that, and it does. Jumps down to line 20. Right, so the for loop ends at line 19, and now we're about to do a++. Okay, a is equal to 4. Let's do the a++. A is equal to 5. And we're about to throw in a null terminator. Where are we putting that null terminator? We're putting it at element bracket 5. Well, the H is element 0, E is element 1, L is 2, O is 3. This question mark is element 4. The second question mark is element 5. That's where it's going to write the null terminator. That's our problem. Where did we want the null terminator? We wanted it to be written where this first question mark is. That's element 0, 1, 2, 3, 4. And A was correct right here before we did that A++. So we're doing an extra increment on A. That's the whole problem. And if we had not done that A++, this would do the right thing. Well, we can exit and change our code and recompile and retest it. But if we really think this is where the problem is, right, and A should be a 4 instead of a 5, we can set it back to 4. So print will actually let us do other things. For example, I can say print A equals 4. And it prints out a 4, but it also changes the value of A to 4. Because when you say A single sign equals 4, that's an assignment. So you can do things with the print statement. So I just changed A to 4, and now when I set my null terminator to be a 0 at element 4, and I return, and I do my print statement, temp equals what it should be. So now I'm confident that's where the problem was. I go out of the debugger, edit my code, change that statement, recompile, retest, and it should work fine. And then I'd reassess and hopefully get 10 out of 10.
Crazy.
Yeah, it is.
That's pretty wild. This would have helped us, like.
Yeah, so I mean, this is letting you get a really up close view of what's going on. And sometimes you've got to do that. Sometimes you cannot find the bug by looking at your code. In 222 in particular, right, we're going to be creating variables while the program's running. And you're not going to be able to tell from looking at the code what's happening when the program's actually running because your memory structure is changing. That's the whole nature of data structure, CSE 222. And so you got to be able to get in there with the debugger and do this kind of thing. So let's go back to the start. And we set temp equal to a bunch of question marks. Well, maybe I want to do something different. Maybe I want a temp to be equal to a bunch of letter A's for some reason. Here's something I can do. I can say print fgets temp 100 standard in. And now it's calling fgets. And it's waiting for me to type something in, like a bunch of A's. And now if I print out temp, it's equal to 19 A's, followed by a new line, followed by whatever's in memory. So you can run functions inside GDB by using the print statement, and that's really powerful. In fact, I can print rem and actually call my function rem and see what happens.
What happens if you put a semicolon in?
I almost did, didn't I? I don't think it does any harm. Oh, doesn't like it. Yeah.
Can you call your other functions?
Yeah, you can call anything pretty much as long as it's been compiled in. And most of standard lib's been compiled
Can you,
in.
like, halfway through include stuff?
No. Like I couldn't say print square root of. Right.
But can you do pound include math.h and then do
If you link with -lm, you should be able to do square root inside here.
Oh, because you would have to compile it.
Yeah, yeah. So yeah, we can do things. Another thing we can do. So let's go back to the beginning. Next. Let's step in here. So so rem was called with two arguments, in and out, right? And it tells us in is equal to this address, out is equal to that address. So we can examine memory directly. So I can say X and give it an address and actually see the contents of memory. And after a while you recognize 48 is the ASCII code for an uppercase H, 65 is a lowercase e, 78 is an X, 6C is an L, and if I just hit enter it'll repeat my X command. 6F is a lowercase o, and then 00 next to that 6F, that's the null terminator. But I'm actually looking at memory now. Just bare addresses.
Wait, I'm not following. Is that backwards then?
So it goes from right to left.
It's in Japanese.
Yeah. So this is our next useful command is X. So this is examine memory. And for example, we could say examine a single byte, and it would show us 48 followed by 65 followed by 78, 6C, 6F, and then an null terminator, and then whatever. Right, so we can look at 1 byte at a time. And we could say let's examine this as a character. So there's our HEXLO null terminator. And look what comes after that. TEMP equals %s \n. Well, that's part of our program. Right? That's not a variable. That's like the string that's passed to our printf statement. It's just sitting in memory next to this other stuff because we never know how memory is organized.
You do.
Well, and you can say examine 100 bytes, and it'll show you 100 bytes in one fell swoop. Yeah. And this is what you have to do sometimes.
Okay.
So I may have told you this before. So the worst bug I ever tracked down took me about 2 weeks to find, and I spent probably about 5 hours a day working on it. So multiply that out. How many hours did I spend? And this is what I was doing. I was stepping through code one instruction at a time. And I would look at the values of the inputs to the instruction. I would look at the current value of the output. I would execute the instruction. I would recheck the inputs, recheck the output, and confirm the instruction did what I thought it would do. And then I went on to the next instruction. And I did that for 70 some hours across 2 weeks before I found the bug. Now that was a hard one because the code I was debugging involved a section of code that was not my own. It was a few million lines of code that I had just taken and was I was building an emulator basically. And so I didn't know what this thing was supposed to do. I had no choice but to go through it one line at a time, sort of the finest granularity possible. But it will get you there, right? If something's going wrong, you will eventually find it. Now, the code we do in this class and in the rest of the sequence, you're going to be debugging code that you wrote. So you presumably will have a pretty good idea what's going on. And there's things you can do other than going one line at a time. For example, I've got all this stuff in the beginning. I know there's something going wrong inside my rem function. I can just say break rem, and I can say run, and it'll skip through everything until it gets to the rem function. And then it'll come back and say, okay, I'm inside rem, what do you want to do? And I can look at this code, and maybe I think my for loop's fine and so on, but I'm not sure if something's going wrong after my for loop. So I could say break at line 20 and continue, and it'll skip through the whole for loop. It'll execute that however many times, and then when it comes down to line 20, it comes back and it says, okay, I'm at line 20, what do you want to do? And now I can look at the value of A, and I can look at my output and so on. So you can go, much coarser granularity if you understand your code. Another thing you can do is you can say something like watch the value of the variable A. And I'm going to say continue, and it's going to run until A changes value. and it's going to say, oh, the old value of A was 0, the new value of A is 1, and here's what I just did. Out A plus plus equals in K. Well, that's the post increment on A. And I can say continue, and it changed from a 1 to a 2, and old was 2, new was 3, 3 to 4, and now it's about to return, and the old value is 4, and the new value is 5. So you can put watch points on variables, and that's useful. For example, something should only happen if a flag is set, and as you understand your code, that flag should never get set. But for some reason this thing is happening anyway, just say watch name of the flag. And as soon as that changes value, you come back in here and you can see what's going on. Here's another thing. Suppose I set up my temp array to be something like this, car star temp equals question marks. If I run that, I get a seg fault. If I GDB this, and I say run, and I say continue, sorry, let's GDB it and say run, I still get my seg fault, right here. But it's telling me where it was. It was at line 19 in rem1.c, out was equal to this, and I was executing this instruction. And I can say print k and print in and print a, and I know where the problem's happening. So now I can run my program again, but I can stop right before I get to that statement, and I can see what's going on. And that's a particularly weird bug to catch, because it has to do with memory organization. We talked about this the other day. When you say car temp bracket 120, that's general memory that you can read write. When you say car star temp equals quote something, it puts it in read only memory. And when we try to modify it, we get a seg fault. All right, two more things really quickly. Suppose I accidentally step into my string copy function. Suppose I accidentally step into my printf function. I start debugging printf, right? It says I'm at line 28 of printf.c. And it doesn't have source code for this, so it can't show me the statement. And now I'm at line 32 in printf.c, I'm 33, and now I'm inside this other thing called vfprintf.c, line 1244, right? This is not what I wanted to do, right? So use the command finish, and that will jump until you get back out of your current function. So I'm back to line 37 of printf.c. If I say finish, now I'm back to my rem1 function. So finish kind of gets you out of stepping when you meant to say next. All right, last thing I'll lead you with is the layout command. If I say layout ASM, it shows me my environment in assembly language. And now I'm looking at the assembly language code corresponding to my C code.
Super gross, dude.
And I can look at registers, and I can step one instruction at a time and do all kinds of really low-level debugging. This is nice for like reverse engineering or hacking or whatever else you're doing for fun that day. Right. All right. So so tomorrow we'll talk about PA4 and any other lingering questions on PA3. No class Friday, and then Monday we'll start digging deeper into string processing, and we'll start looping back to pick up some more Linux stuff. All right, have a good one. I'll see you next time.
Thanks, Nick.
Yeah.
Yeah.
Okay.